Good evening to all. Okay, so today's session will be totally based on the fluid mechanics. Okay, so in the fluid mechanics, we will be seeing the most important topic. Good evening to all. Okay, so today. Okay, so the session will start with just I will tell you the introduction. Okay, I will tell you the introduction why fluid mechanics is important. Okay, let's start the session. So fluid mechanics basically deals with the transportation of a fluid from one point to another point. Okay. It deals with the transportation of the fluid from one point to another point. Okay. From one point to another point. This. Okay. So here we will deal with that our main aim is with the delta P. We have to optimize this delta P. That is the most important thing here. And when we are optimizing this delta P, okay, please make sure that okay, pumping cost should be reduced. Okay, pumping cost should be reduced. Okay, pumping cost should be reduced. Once the pumping cost is reduced, okay, it is going to help us in various section. Okay, that is ultimately we are going to save the energy. Okay, so here we will see on the basis of different types of fluid, most expected question first we are going to see. Okay, so here we will see first types of fluid. Okay, on that there is a one question based on the whether the fluid is dilatant, okay, pseudoplastic, or it is a Bingham plastic. Okay, based on this we have to select the fluid. Okay, so how the question can be asked from here, that the generalized equation is tau equals to k dv by dy to the power n minus 1 dv by dy. Okay, and the ratio of this shear stress, okay, and the ratio of the shear stress and shear strain will give you apparent viscosity. Okay, it will give you apparent viscosity. Okay, so let's solve one question. The apparent viscosity of fluid is by 0.007 dV by dy to the power 0.3. Okay, where dV by dy is velocity gradient. Okay, so you have to check which type of this fluid is by comparing this equation. Okay, so please check. Okay, So if you compare this, okay, if you compare this with our generalized equation, then dv by dy is equals to n minus 1, and what is given in the question, dv by dy is 0.3. Okay, so n will be 1.3, and when n is coming greater than 1, it means the fluid is dilatant. It is a dilatant fluid. Okay, it is a dilatant fluid. So such questions can be easily asked in the GATE examination, because if n is less than 1, then it is pseudoplastic. If n is equals to 1, then it is Newtonian fluid. And for Bingham plastic, you have to this tau equals to tau naught mu dv by dy. This is yield stress. Extra stress will be required here. Okay. So in this way, we can solve this question on the types of fluid. Then on the basis of static fluid, question can be asked, a dam of width 50 meter is used to hold water in a reservoir if the water height is 10 meter from the bottom of the dam. What is the total force F acting on the dam due to water? Solve this. So basically there is a dam, okay, and the water is there. So as the water is not moving, it means the fluid is in static mode. Okay, so how we will solve? Force is mass into acceleration, but here in terms of height, so we will write h rho g. Okay, so here we will use force is equals to pressure into area. Okay, so we have two formulas for force. So here pressure, we know static pressure is h rho g into area 50 into dh, height is changing. So F is equals to 50 rho g, and the height is changing from 0 to 10 hdh. So force is equals to 50 rho g s square by 2, 0 to 10. So F is equals to 50 rho g. Okay, 10 into 10. Okay, so if you solve this, what is the answer is coming? Answer will come 25 into 10 to the power 6. So this is the amount of force will be exerted. Okay, so like this, there are the questions from the static. Okay, so here in the question, they have clearly mentioned, okay, that height is 10 meter from the bottom of the dam. Okay, and it is reservoir. So we know that in reservoir, the fluid is not moving. So from this, you should have an idea. So we will write both force formula, and according to the data, we will calculate force. Okay. Next question. The relation between the stress tau and strain rate du by dy for the rapid flow of a granular material is given by tau equals to b dux by dy square, where b is constant. If m, l and mass, length and time dimensions respectively, what is the dimension of constant b? Okay. So calculate this. So here tau is equals to b du by dy to the power square. So b equals to tau du by dy whole square. What is tau? Tau is force acting per unit area. What is force? Mass into acceleration. So mlt minus 2. है ना? Mass is m and acceleration is meter by second square. So like this you have to solve. Area is L square. So it will be m L minus 1 T minus 2. And du by dy is equals to L T minus 1 upon L. So it will be T minus 1. Okay. So b equals to m L minus 1 T minus 2 upon T minus 1 whole square. So b equals to m L minus 1. So in this way, means you have to calculate the dimensions in the basic form. Okay. In the basic form, you have to calculate the dimensions. Okay. Next question. In the laminar boundary layer, flow over the plate the ratio del by x varies as. So this is the most frequent question. Okay. Means gate has asked this question I think 10 to 12 times. Okay. So this is from the boundary layer actually question. Okay. This question is from the boundary layer. So for boundary layer in the laminar flow, Bloss's equation is used, and that is del by x is equals to 4.67 upon under root of Rex. Okay. So here we can say del by x is 1 under root of Rex. And you often open this, suppose rho v d we will take as x upon mu. Okay. So here it is 1 of x upon under root of x. It is del. So if you say this, cancel this, what will be there? Del is directly proportional to under root of x. So here you can say it is x to the power 0.5. This question GATE has asked so many times. Okay. Once they have asked from the turbulent flow also. So remember, this turbulent flow is directly proportional to x to the power 0.8. Now applying a delta P across a capillary result in a volumetric flow rate Q under laminar conditions. The flow rate for the same delta P in a capillary of a same length but half the radius is so here we know that Q is directly proportional to D to the power 4 for laminar flow. Again, this question is asked so many times in the GATE examination. So Q is directly proportional to D to the power 4, and here they are saying that it is half. So 2 to the power 4 is 2 into 2 into 2 into 2. Hai na? 4, 4, 16. So it will be Q by 16. So like this. So this question also GATE has asked so many times. Okay, so I will give you one good question. Please solve this. In a Bingham plastic fluid of viscosity mu is 10 Pascal second and a yield stress tau naught is 10 kilopascal, is sheared flat plate, parallel plates separated by a distance 10 to the power minus 3 meter per second. The top plate is moving with a velocity 1 meter per second. The shear stress on the plate is okay. So here the fluid is Bingham plastic. So we know that for Bingham plastic it is tau equals to tau naught plus mu dV by dy. So tau naught they have given 10 into 10 to the power 3, mu viscosity 10, velocity 1 upon 10 to the power minus 3. The answer is directly coming 20 kilopascal. And here just you have to remember the formula. Okay. In a fully turbulent flow, Reynolds number greater than 10 to the power 5 in a pipe of diameter d for a constant pressure gradient, the dependent of volumetric flow rate of an incompressible fluid is d square d 2.5 d4. Solve this, what will come? So if you see this, area is pi by 4 into d square into velocity. So the most important formula you have to remember that for pressure drop it is delta P equals to 4FL rho V square by 2D. Okay. So in terms of D we want, so here from this formula if you see V square is directly proportional to D. So V is under root of D. So here it is under root of D will come, and from here it is D square. So it is D to the power 2.5. So here the answer is correct, 2.5. Here there is a one condition we can say that here F, okay, here F is also a function of Reynolds number, and Reynolds number is also a function of diameter, but here we are not taking consideration of that part. Okay, so that you make sure. Otherwise, you will end up with a wrong answer. Okay, here we are not considering this, that f is the function of Reynolds number and Reynolds number is a function of diameter. Got this? Okay. The equivalent diameter for flow through a rectangular duct of width b and height h is option A, hb upon twice h plus b, hb upon h plus b, twice hb upon h plus b, 4hb upon h plus b. So here equivalent diameter formula is 4 into hydraulic radius. Hydraulic radius is flow area upon weighted parameter. Okay, so flow area is twice AB. Weighted parameter will be, see, weighted parameter is like this. Okay, so this is this twice A plus B. So here AB is HB, height into breadth. So 4 into this cancel. So it will be twice HB upon H plus B. C option is correct. Okay, like this. Next, very good question, which is again very time the gate has asked this. What is the force required in Newton to hold a sphere, spherical balloon stationary in water at a depth of h from the air-water interface. The balloon is of radius 0.1 meter and is filled with air. Solve this. This is again question from a static fluid, you can say. So here force equals to 4 by 3 pi r cube density of water into gravity minus 4 by 3 pi r cube into density of air into gravity. So we know that density of water is very greater than density of air. So we can write this force equals to 4 by 3 pi r cube into density of water into G. R value is given. So from here, F equals to 4 by 3 pi G. This is the thing. Okay. So here basically to balloon will come upward. Which force is applying? You can say it is a buoyancy. So by what is buoyancy? Volume of object into density of fluid into gravity. So that is the same thing we have written here. Okay. Got it? And the most important topic from the gate point of view is the Bernoulli's equation. Okay, so Bernoulli's equation, you can say it is the energy conservation. Okay, Bernoulli's equation is all about energy conservation. That at every point when the fluid is flowing from one point to another point, it consists of some energy. And according to thermodynamics second law, we can say that energy neither be created nor be destroyed. It can be only converted to one form to another form. Okay. So here the question is a pipeline system carries crude oil of density 800 kg per meter cube. The volumetric flow rate at point 1 is 0.28 meter cube per second. The cross-sectional area of the branches 1, 2, and 3 are 0.012, 0.008, and 0.004 meters square. All the three branches are in horizontal plane. And the friction is negligible. If the pressure of the point 1 and 3 are 270 kilopascal and 240 kilopascal, then the pressure point 2 is okay. So diagram is given. Inlet 0.1, outlet 0.2, this is 0.3 outlet, 1, 2, and this is 3. So try to solve this. So if you see, they have given the cross-sectional, 3 cross-sectional area. Okay, so try to apply the Bernoulli's equation here. So here 3 cross-sectional areas are given. One flow rate is given. So basically we can write one equation from the continuity equation, and 2 pressures are given. So if the pressure of point 1 and 3 is given, so this and this is given. So you can apply the Bernoulli's equation here. P by rho plus V1 square by 2 plus Z plus Z G NWP is equals to P by rho plus V3 square by 2 plus ZC plus HF. This is frictions. Okay, HF. So there is no data regarding friction, 0. There is no pump. Okay, the pipe is horizontal. So these all terms will be 0. Okay, now you can solve easily this terms. P by rho, data is given 270. So 270 into 10 to the power 3, something rho, whatever is given. Okay, velocity V1 is given, and you can see the flow rate is given and the area is given. So you have a formula A1 V1 is equals to Q. So Q is given, area is given. So you can calculate V, and that will be here. Similarly, here again the pressure is given 240 kilopascal by 1000. Okay, and you can calculate V3 from this equation actually. Okay, you can calculate the V3. Now you can write the continuity equation that A1 V1 is equals to A2 V2 plus A3 V3. Okay, because you see the A3 V2 and second point and third point are outlet. Okay, so here you have A1 V1. Now you have A2 V2, A3 is given. So you can easily calculate the V3. Okay, sorry, V3 will come from here. From this equation, you can calculate V2. And we want the pressure at second point. So now again apply the, Bernoulli's equation at point 1 and 3. Sorry, 1 and 2, because we want pressure at point 2. See here, point 2. So again, same data here, 270 into 10 to the power 3 upon 1000. You have V1 square by 2 is equals to pressure. You have to calculate density you have, and V2 you have calculated from here. So V2 square by 2. Now from here, you will see that you will get a value of P2, which is coming 284 kilopascal. Okay, so you have to think in this way, because see, there is a difference between the Bernoulli's equation and the continuity equation. Bernoulli's equation is basically about the energy conservation between only 2 points. You can't apply the energy conservation between 3 points. Okay, because as the pressure is automatically fixed, okay, as the pressure is fixed, okay, sorry, I will say that as the pressure is fixed, automatically the velocity for that part is fixed, okay. So means for that velocity pressure is fixed and vice versa, for pressure that velocity is fixed. So it means if you have one data you can calculate it, okay, from this, because see it is the energy conservation means this part 1 should be equals to this part 2. So if pressure is going to reduce, okay, obviously if the fluid is moving from point 1 to another point, the pressure is going to reduce. So if pressure is going to reduce, obviously this part has to be increased. This is compensated by increasing the velocity or by increasing the z value, but here the z value is 0. So obviously the velocity will increase like this, okay. And Bernoulli's equations are the most favorite part of the gate examination, okay. Okay, one more question we will solve. A siphon tube having a diameter of 2 centimeter draw water from a large open reservoir and discharges into the open atmosphere. Diagram is given. Okay, so you have to calculate the velocity in meter per second at the discharge point. Okay, so calculate this. Okay. So if you see this question, say this. This box has a, okay, this box has a potential energy. Why? Because here the water is at static position. Okay. And this point is open to atmosphere. So we have P by rho plus V1 square by 2 plus GZ plus NWP is equals to P by rho plus V2 square by 2 plus GZ plus HF. So no data regarding friction, no regarding pump, as both are open to atmosphere. So this is cancelled. So if you see the first point is at static position. So it means fluid is not moving. So it is again 0. But it has a height of 2 meter because it is potential energy. So it is 2 into 10. And this V square, again, this is the ground level. Okay, this is the ground level. So again, this is 0. So into 2. So this will come V2. Okay, because at second point, the velocity is moving. It means kinetic energy is, here potential energy is 0. Okay, at point 2, potential. So see here, it is 2 meter and it is coming, total length is 5 meter. So you might be thinking that why we are not taking 5. Okay, why we are not taking this 5. Okay, why we are not taking this 5. Okay, this is, this is 5 meters, so here it will 5 will come. Okay, why we are not taking 7? 5 plus 2, 7. Because if you see, this pipe is moving 2 meter upward and then again the 2 meter downward. Okay, so here this 2 meter upward and 2 meter downward will cancel. Okay, because that much amount of energy is needed for up and again down is there. Again, second point is that this 2 meter is up. Okay, and how much potential energy this system have? This is 5 meter. Okay, this system has a potential energy of 5 meter. So only energy neither be created nor be destroyed. It can be only converted to one form to another form. Means this has a potential energy of 5 meter. So this will only convert to the kinetic energy, and the kinetic energy is the function of velocity. Okay, this is the thing. Got it? So most of time you may do mistake by 5 plus 2. Don't do like this. Okay. Okay. One more good question from the Bernoulli's equation. A pump draws oil of specific gravity 0.8 from a storage tank and discharges it to an overhead tank. The mechanical energy delivered by the pump to the fluid is 50 joule per kg. The velocity at the suction and the discharge point of the pump are 1 meter per second and 7 meter per second respectively. Neglecting the frictional losses of assuming kinetic connection factor to be unity, the pressure developed by the pump in kilonewton per meter square is. Calculate this. Again, this is a very good question. Okay. So here again we will apply our formula P by rho plus V square by 2 plus GZ NWP equals to P by rho plus V square by 2 plus GZ plus HF. So here let's see what is the data. So you have to calculate the pressure developed by the pump. So see, pump is like this. Okay, pump is like this. It means it will be, okay, it means it will be horizontal. It will be horizontal. So here the Z terms are removed. Okay, here Z terms are removed. Okay. Z terms are removed. Velocity, if you see, okay, first this 50 joule per kg. So this is the mechanical energy, means this WP value is given 50. Okay, this is given, and velocities are also given 1 meter per second. So this data is also given. So see, and HF, is there any data? HF, neglecting frictional losses. Okay, it is neglecting frictional losses. The HF is 0. Now you can easily calculate the delta P value as this is given. All the values are given, and this is obviously delta P will be positive. To solve this, it will be coming 20.8. So see here, what is important is that when you have to neglect the pressure when both the tanks are open to atmosphere, only at that condition you have to neglect. है ना? Only at that condition you have to neglect this. Okay, here it is pressure drop across the pump, so you can't neglect it. Okay, so these things you have to take care while solving the question. Okay, while solving the question, these things you have to take care. Okay, so here P2 minus P1 you will get the answer directly. Okay. Got it? Okay. A free jet of water is emerging from a nozzle diameter 75 mm attached to a pipe diameter 225 mm as shown below. Okay, so it will be like this. 21 meter is this, and this is the length of 0.5 meter. Here the pipe diameter is 225 meter. This is nozzle tip. Okay, so this is point A. And this is point B. Okay. So velocity is given at point A, that is 18 meter per second. So we have to calculate this velocity. Velocity at nozzle, you can say. Okay. So if you want to calculate this velocity, it means you have to apply the, again, Bernoulli's equation. Okay, you have to apply the Bernoulli's equation. So here we will write pressure at nozzle into rho g v square by 2g plus z. So here the unit is meter we are writing. If you see previous question, their unit is joule per kg. Okay, here also you can write joule per kg or anything else. Okay, it's your choice. Nothing will change. Again here pressure at point A, because there is no pump. Again rho g, velocity is given and za is given. So if you see what are the points, z is given, yes, this data is given. Okay, both are open to atmosphere. Okay, so again these terms are cancelled. So this is 0. Now you can easily calculate this velocity. Okay, you can easily calculate this velocity. Okay, you can easily calculate this velocity because all data is given. Okay, so if you calculate this, velocity of nozzle will come 27.1 meter per second. What is important is here is that you have to neglect this pressure terms. Because if you see in the previous question, we have not neglected this pressure terms because we have to calculate delta P across the pump. Here the pressure is at this points. Okay, so both are at open to atmosphere. Both are open to atmosphere. You can also calculate the gauge pressure at this point, at point B. Okay, so now you will apply the Bernoulli's equation between this point B and this nozzle tip. You can easily apply. Okay, so Bernoulli's at point B upon rho plus VB square by 2 plus ZB. There is no pump, so you can write it is nozzle by rho plus Vt by 2 square plus Z. Okay, so what is the distance here? This is 0.5. Okay, this is 0.5 here. Okay, now here you know diameter is given. Here you know the diameter. So A1 V1 is equals to A2 V2. So you can calculate the velocity at B. Okay, once you calculate the velocity at B, you can calculate PB minus PT. See here this PB and PT are always an absolute pressure. Okay, it is always absolute pressure. What is absolute pressure? It is gauge pressure plus atmospheric pressure, है ना? So see here at PB gauge plus ATM, PT gauge plus ATM. So if you see this diagram, PT is at atmospheric means gauge is 0. So if you minus this, what will come? Gauge plus ATM minus ATM, है ना? So this ATM is cancelled. So basically, whenever we are calculating gauge pressure and one at atmospheric, so here the delta P is nothing but it is a gauge pressure at point B. Okay, and you can easily get this. Okay, so PB by rho minus PT by rho is equals to VT square by 2 minus VB square by 2. This will give you the direct answer. So if you do this PB minus PT, it will give you 367.6 kilopascal. See, calculating answer is not important. Important is how you calculate and what is the approach. That is the most important thing. Okay. So you should not be confused between absolute pressure, gauge pressure, when pressure terms will be cancelled, when pressure term will not be cancelled. Everything. Okay. Everything you should be take care of. Okay. Okay, so hope you have cleared your all doubts. So here we are only taking the most important questions. Okay, so this is 100% sure that you will get one question from the Bernoulli's. Okay, you will 100% there will be one question from the Bernoulli's part. Okay.